Welcome to this video. Our focus is on the working fluid that enables heat transfer in vapor compression systems, the refrigerant. We'll explore its properties, types, and environmental impact, as well as how it's used in a wide range of HVAC systems in real-world applications. In this video, we'll begin by answering a fundamental question. What is a refrigerant, and how does it function in the vapor compression cycle? We'll then examine the main categories of refrigerants used in HVAC systems, how they are classified, their thermodynamic and environmental performance, and the transition from older substances like CFCs to modern alternatives such as natural refrigerants and HFOs. Finally, we'll look at the key factors engineers must consider when selecting a refrigerant, including efficiency, safety, and compliance with environmental regulations, such as the Kigali Amendment. The learning objective for this video are compare different refrigerants based on thermodynamic, environmental, and safety criteria, and then reflect on the environmental impact of refrigerant selection in the context of sustainable engineering practices. But let's begin with a question. When engineers or manufacturers select a refrigerant from an HVAC system, what factors do you think they prioritize? Think how to make this prioritization of what refrigerant to buy. It is efficiency, safety, environmental impact, or something else. Take a moment to think about it. In this video, we'll explore what refrigerants are, how they differ, and why that matters for both performance and sustainability. A refrigerant is a fluid specifically chosen for its ability to efficiently absorb and release heat as it circulates through the vapor compression cycle. It operates by undergoing phase changes, evaporating to absorb heat at a lower pressure in the evaporator, and condensing to release heat at high pressure in the condenser. This cycle of phase change is driven by pressure and temperature variations managed by the compressor and expansion device. The selection of a refrigerant affects system efficiency, safety, and environmental impact, especially in terms of ozone depletion and global warming potential. In sustainable engineering practices, understanding how refrigerants function and their long-term consequences is essential to design responsible HVAC systems. Refrigerants are categorized by their chemical composition or environmental characteristics. Older refrigerants, such as CFCs like R12 and HFCs like R22, were effective and widely used, but they cause significant damage to the ozone layer. These substances have been phased out under international agreements such as the Montreal Protocol. Hydrofluorocarbons, HFCs, such as R134A and R410A, replace them and have no ozone depletion potential, but they come with high global warming potential, prompting the new regulations and phase downs. In response, natural refrigerants have gained attention. CO2, that is called R744, is used in supermarkets and heat pumps. Ammonia, with the denomination R717, is favored in industrial refrigeration for its efficiency, and hydrocarbons like propane, R290, are common in domestic systems. More recently, hydrofluoroolefins, HFOs, such as R1234YF and R1234CE, have been introduced. These refrigerants offer low GWP and zero ozone depletion, making them promising candidates for future sustainable HVAC applications. However, some concerns remain regarding their atmospheric degradation products, particularly trifluoroacetic acid (TFA), which may persist in the environment and could pose long-term ecological risks. When choosing a refrigerant, we must balance several independent factors. Thermodynamic performance determines how effectively a refrigerant can transfer heat and how it influences component sizing, compressor work, and system pressure. For example, ammonia has excellent performance, but it requires careful handling. Safety is also paramount. Some refrigerants are flammable, like R290 propane, or toxic, like R717 ammonia. So the application and building type strongly influence acceptability. Environmental considerations, including ozone depletion potential (ODP) and global warming potential (GWP), are now major selection criteria. International agreements such as the Montreal and Kigali amendments have restricted and phased down high ODP and high GWP refrigerants, pushing industry toward alternatives that are safer for the planet. To summarize, refrigerants enable the phase changes and energy transfer that drive the vapor compression cycle. Without them, no heat transfer would occur. The wide variety of refrigerant types presents trade-offs in performance, safety, and environmental impact. Each selection must consider the specific application and regulatory context. In sustainable HVAC design, refrigerant choice is a long-term decision that affects not only operational performance but also our environmental footprint as engineers and practitioners. You completed this lesson. Great progress so far. To continue building your understanding, check out the next videos in this course. We'll look into how real refrigeration cycles deviate from the ideal and what enhancements can improve their performance. Then we'll explore strategies for boosting energy efficiency and integrating smart controls to optimize HVAC systems in practice. Let's keep learning.